Yeah. You know, yeah, and it's basically it's what you can get away with, I guess, when you have a whole bunch of very tolerant friends.
That's true.
Right, because that's pretty much what you would do. Ardash would just like show up at somebody's door and like often unannounced, to be like,
oh, I see.
Yeah, seriously.
That's all right.
Oh no. I've been here since came in on Monday.
Oh, I see. Why that's you?
Yeah, yesterday wasn't feeling it. So
I see.
I just stayed home and I worked on some grant applications.
Okay.
Yeah, I think this will be this is the second or third time.
Wait, really? What? You saw the one by Leo or John?
No, didn't you do it? The CFAR meeting or something?
Oh, I get that.
All right, cool. That's a sure sign that I'm going to too many conferences.
We're pretty good at healthcare. That could be that you listen to either
Or just had a senior moment. All right, let me go bug people.
Yeah. What do you think?
Let's give them a minute or two to pour in and then get started. Step by step. All right, well, thank you very much, everybody, for coming back. I hope you guys gorged yourself on those amazing chip things as much as I did. But in any case, it's my real pleasure to have Robert Huang here. Robert, take it away.
Yeah. Thank you so much for inviting me here. Today, I'll be talking about local minima in quantum systems. This is a joint work with Anthony Chen, John Preskill, and Leo Zhou. So we all have this hope that quantum computing can advance physics, chemistry, material science by solving the ground state of quantum systems. However, at the same time, we all know that finding ground state is QMA hard, and hence ground states are both classically and quantumly hard to find. This QMA hardness of finding ground state implies that ground states are not always very physical, particularly if we assume that nature cannot efficiently solve NP hard problems, which a lot of experimental demonstrations have already shown, then nature should not always be able to find the ground state of the quantum system. Now one could ask, when we have a quantum system that is cooled in a very low temperature thermal bath, what would the system actually thermalize to if it doesn't find the ground state? In general, the system would find a local minimum of the energy. For example, like the plot shown here, if we start from a state that's, say, closer to this suboptimal local minimum, then when we cool it down, it will actually get stuck into that local minima instead of the actual true ground state. However, if we start from a point that's closer to the ground state, then perhaps it will go to the ground state. And for some physical system, it is well known, for example, like in spin glasses, that the system almost always finds suboptimal local minima instead of the true ground state. And hence, in some of these systems, ground states are physically irrelevant because we cannot meaningfully find them, nature does not find them, and hence the physical properties of these systems are not determined by ground state, but by these local minima. So together, this raises the following question, which is the main question that we study in this work, which is how tractable, if we now turn our attention away from ground state and talk about local minima, then how tractable is the problem of finding a local minimum in quantum systems using either classical or quantum computers? So that's the main question that we were hoping to answer in this work. However, in order to formally answer this question, we have to first present a formal definition of local minima in quantum systems, which quite surprisingly, previously it has not been properly formalized before, even though a lot of physicists, chemists talk about related concepts. For example, metastable states or false vacuum, they're all just the same as local minima. Now, what we were going to do in the following talk is we will first present a formal definition of it, provide a characterization of these local minimum, and talk about the complexity, the computational complexity of finding local minima. So here's the outline. Start by defining what quantum local minima are, talk about the complexity, and finally ends with future directions.
They should have a succinct plus description.
I don't think it, in general, I don't think they would have, they might not have a succinct classical description. So when we talk about the problem, or when we, in the later part, talking about the computational complexity, we'll be focusing on more like a relational problem, in the sense that we just wanted to output a local property, like a local observable on any local minimum. So we're going to define that, so then it will have classical input and output. But in general, local minimum can be, yeah, like the Hilbert space is vast. They might not have succinct classical description. They're just some crazy high complexity quantum state. So let me begin with defining what local minima are. Of course, this is our definition, but hopefully everyone would agree. We feel that our definition is natural. So given an n-qubit Hamiltonian H that we write out as a sum of few body terms, and hence this Hamiltonian can be described succinctly on classical computer, we say a local minimum of the Hamiltonian H is an n-qubit state rho, such that it has a minimum energy under any small perturbation to the state, kind of following the definition from classical optimization.
Well, is that even correct? Because couldn't you just perturb yourself from the towards the global ground state in a small way, and then it wouldn't be local in that sense?
That's right. So here, this is just a high-level definition. I haven't talked about what perturbations are, which I'll get into detail. So if one allow any perturbation, then yes, then you can always do it. But here we're going to focus on perturbation of the following form. We're going to think of perturbation PA, P alpha, where it's parameterized by a vector alpha that takes states to states. So for example, if we start out, so let's say if this alpha vector is 0, then P0 would just be an identity map. And when alpha vector is small, we think of P alpha as close to identity map, depending on how small alpha is. But in general, it would just be a mapping that takes density matrices to density matrices. And we're going to think of these perturbations to be parameterized by this vector alpha, which is of polynomial size. So if we make this restriction that the perturbations are polynomial size, then we will not, in general, be able to just do any unitary rotation to just turn that local minima to a direction that's close to the ground state. So, but we're going to place more constraint. And furthermore, we're going to define this notion of an approximate local minimum. And we call it an n-qubit state rho to be an epsilon approximate local minimum of H under this perturbation P if the original state, the energy of the original state, trace of H rho, is less than or equal to the energy of the perturbed state with a small error epsilon times the norm of alpha. So for example, if epsilon is 0, this would just be an exact an exact local minimum. And an exact local minimum would be that trace of edge rho is less than or equal to trace of edge, the perturbed state. The intuition that we have before.
Even M is one dimension, you can still push towards the true ground state, right?
Yeah, but we were thinking of it as the perturbation, like this P alpha would just be a fixed object. And particularly later on, we're going to talk about these perturbations. I mean, here as defined, the set, or maybe the next slide would be clear. This local minima would form a subset of the entire n-qubit state space. And this subset would contain a ground state, but it also depends on the perturbation. So if one creates some crazy perturbation that says, I always just take from any state and then just kind of push it to the ground state. If I define the perturbation that way, then there will be no local minima.
Parametric family, yes. Have a restriction on how you parameterize.
Yes. Particularly, we're gonna, after this slide, I was gonna talk about two natural classes of perturbations. And from there, it will be clear that, that this in general cannot be done.
So in some sense, when you're defining this over here, are you kind of assuming that imposing some sort of a metric on your space? And
Yes.
Saying that basically for any vector that perturbs it that's less than radius r in that you demand that its energy will be going up.
Yes, that's right. Okay, so yeah, any more questions on this definition? So yeah, just to provide some, let's say this is like a 1D thing, then showing onto there. Then if we have a small epsilon, then this local minima subset will contain, for example, a small neighborhood around the ground state, as well as a small neighborhood around that suboptimal local minimum. And as this epsilon decreases, they will shrink down into these 2 points. That's one way to think about this. Okay, so now let's talk about what these perturbations are. Because in general, if we just have an arbitrary unitary perturbation, then there will be no local minimum, because one can always just perturb it to the ground state. So what we focus on, we essentially focus on two, corresponding to a closed system perturbation and an open system perturbation, or we give it the name local unitary perturbation and thermal perturbation. So first, let me talk about this local unitary perturbation, which has actually been studied in this field. There's an old paper, which I'll talk about, that give essentially the same definition. So this is rather mathematically natural. The idea is the following. Let's say we have a pure state and pure state psi. These perturbations, they correspond to just perturbing psi according to this Hermitian evolution. So we say, for example, fix a collection of m few body Hermitian operator. Think of them, for example, as all possible, say, 2-qubit Pauli operator. And now it would define this generating set. And then now when we do a perturbation, we would just evolve it under some weighted sum of these Hermitian operators. And one can easily show that when we have any quantum circuit with near identity 2-qubit gate, this will correspond to a local unitary perturbation. Okay. And this essentially forms a metric over the space of over the entire pure state space. And particularly, there's this old paper from almost 20 years ago called Quantum Computation as Geometry, where it shows that by defining these perturbations, it forms a Riemannian geometry, and then we can talk about its geodesic and so on. And essentially, a local minimum here is just a local minimum according to this metric. So you can think of it as there's a bunch of states, and if one state, when you perturb it using some 2-qubit gate, it would be connecting to another state, then they're in the neighborhood. That's what this local unitary perturbation essentially entails.
And the goal is to describe some sort of geodesics.
Oh, I mean, that paper is about, yeah.
What did they say about geodesics?
I think they were saying like, oh, if you wanted to
It gives the shortest circuit effectively that carries out a particular transformation.
Observe the lower bound.
Yes,
Yes.
but unfortunately, it's totally useless.
Yes.
But it's beautiful.
That's the take home.
Yeah.
And published in Science.
Yeah.
Yes.
You'll notice it's not a journal, it's science.
Yeah.
Yeah, it's an interesting concept, and it kind of naturally, it's pretty mathematical in nature, but not entirely sure why you wanted to. I mean, for them.
But it's an awesome paper. Everybody should read it.
Yeah, but I mean, here in.
There was a lot of interest at the time about what is the minimal number of gates you need to do something to make a universal operation. Minimum number of operations, I think it was a related to that.
That's right. Yeah, but this is one definition of perturbations. Which from one could also argue, like from a more variational quantum algorithm perspective, these are also the natural perturbations that happens. Like you have a quantum circuit and you try to perturb your state. You have a unitary quantum circuit, you try to perturb your state, it will correspond to this local unitary perturbation.
But this is not going to cover all the possible states, right? It's really like a very thin low dimensional manifold in this high dimensional space, because it's really only have m degree freedom.
Yes, but you can define this whole geometry over the entire Hilbert space.
But from a fixed starting point, you can only reach to a very small set.
What do you mean? Like because yeah,
from this ensemble, you can only reach a very low dimensional manifold in also state space.
that's right. That's right. That's right.
It's not really a metric because in many other directions, the distance equal to infinity.
I mean, that's how, like, you can have a manifold that's living on a much higher dimensional space, and that's just.
Well, I'm saying that you can only reach a very low dimensional subspace of the potential.
Only in the tangent space, yes. In the close by neighborhood, yes. But you can keep moving, and then you can go to whatever state you want. It's a connected space. Because like you can generate any state.
You can generate any state with a fixed set of HA.
Yeah. Like 2 cubic gates. Like 2 cubic gate is known to be universal. So.
The algebra is better.
Yes. Yeah, so you just kind of keep composing it, then it will go there. Using one, like, yeah, in the tangent space, it would not, but then you can just keep composing it, and then one could get to any. But in general, if you wanted to go from one pure state to another pure state, you would need an exponentially long time. Oh, sorry, can you speak louder?
Can you speak up?
I mean this HA? Yeah, you can think of these HA just be all possible 2 qubit Pauli. Like they're just 2 qubit Pauli terms. They're the entire collection of around order. Yeah, in that case, M would be order n squared.
So that's the number not close.
The number will what?
So like the set of all possible this kind of evolution is not closed. Because
Yes, this is only a closed dynamics. Is that what you're asking?
So I think, yeah, so this is a set of generators that generate the whole the algebra. So like this set itself is not closed in terms of the algebra.
Yes. I see. Yeah, thanks. Yeah, but this is really just like a normal quantum circuit. Any quantum circuit, you can write it out as a series of perturbations that look like this. It's a closed system. It's a unitary quantum circuit. That's this local unitary perturbations. It defines a geometry. But then we also know that from a more physically motivated perspective, the right definition of perturbations are not necessarily unitary. Because when we have a quantum system that is placed in a low temperature thermal bath, the perturbations are described by an open system dynamics, by these thermal invariant dynamics instead of a unitary dynamics. And these thermal embodiment dynamics are generally irreversible, meaning that they're non-unitary. So this is the second family of perturbation that we will study. And just to recap, which I think most of you would probably already know, that from modern quantum thermodynamics, there are two macroscopic quantities, the inverse temperature beta and the characteristic time scale tau. And now suppose we have this system and environment that is being coupled by the few body operator AA. Then for each of them, it would generate a Lindbladian, this LA, corresponding to them, which is essentially the operation after we traced out the environment. Like we assume they're weakly coupled, and then we trace out the environment, then the dynamics on the system will be governed by this thermal Lindbladian. And now we consider thermal perturbation kind of similarly. We consider all possible different few body operator. Say these AA can be single qubit Paulis or 2 qubit Cal Paulis, and then we can essentially define the perturbations as a linear combination of these Lindbladian terms.
So at this stage, is there a reason to focus your attention on Lindbladians rather than more general CPTP maps?
One could also consider that, but here I would say the reason we were focusing on this is that it more naturally matches this idea that if we have a quantum system that is placed in a cold bath, then the perturbation that will be done on the system will be governed by these specific Lindbladian dynamics rather than a more general one. So I would say it's more like that. So now just to summarize the definition, we say an uncubic state rho is an epsilon approximate local minimum of the energy of the Hamiltonian H under perturbation P if the energy is after perturbation is greater than or equal to the original one up to a small error epsilon. And we've defined two families of perturbations. One was based on local unitary perturbations, which are just closed system perturbation, which is mathematically natural and is reversible, and it corresponds to Hermitian evolutions. We also briefly talked about these thermal perturbations, which are more physically motivated. They're irreversible, and they correspond to closed open system dynamics or Lindbladian evolutions. And what I'm going to do next is that I'm going to talk about, for these two families of perturbations, what is the complexity of finding local minima. So in order to talk about that, as Umesh was asking, we need to first define some a proper problem with inputs and outputs. So we would say an algorithm solves the local minimum problem efficiently if for any n-qubit local Hamiltonian H and any local observable O, the algorithm can output the expectation value of the observable O of any epsilon approximate local minimum rho of H in polynomial time up to an inverse polynomially small error. So note that this is a relational problem in the sense that if, for example, the Hamiltonian has multiple different local minimum, then the algorithm will be correct if it just outputs one of them.
One thing I wanted to get here is your notion of locality for the Hamiltonian and your notion of locality for the state perturbation. They seem like they're different, are they? Like when you say local Hamiltonian, I assume you mean K-local.
Yes, I'm assuming constant local.
But your perturbation that you're doing isn't really of that same form.
Yeah, so here this alone still has to be parameterized also by what are the perturbations one can allow.
I was just kind of wondering whether or not these are like the same notion of related or literally the same notion of locality.
In the way we're focusing on, they're the same. So for example, these are few body local Hamiltonian, and then we will consider perturbations that are also few body local. Yeah. So I can see that this problem has purely classical input and classical output, and hence we can compare what if we now have a classical algorithm that try to solve this problem versus having a quantum algorithm to solve it. Is there a question?
Is rho itself considered a local observable? Like if I replace rho with rho itself?
Oh, yeah. So here, when I say local observable, oh, I meant like that observable acts on most qubits as identity and only acts non-trivially on a few qubits. And hence, in general, a quantum state role would not be a local observable.
Why is the input classical?
Yeah, because the input, so the input to this problem is the Hamiltonian as well as the local observable. I mean, not quite, because we also need to specify the perturbations, but as we talked briefly about it, the perturbations just corresponds to, like, for example, what are these few body operators, or what are these few body Hermitian operator, which can all be described classically. I mean, they're kind of quantum object, but they're few bodies. So one can have a 16 classical description. And here we're focusing on local Hamiltonian, and hence that also have 16 classical description. Hence, it's a purely classical input problem.
Yes. So one question. So previously you mentioned that here the local perturbation you consider essentially means it's like a field body local. But previously you mentioned it basically means your vector alpha, the norm of alpha is very small. How to connect these two?
Oh, are you saying, like, I guess you're asking something
Yeah, right.
here.
Right.
You're saying the alpha m is a polynomial size, like polynomial dimension vector, yes?
This is essentially what you mean by field body local perturbation.
Oh, yeah. Here, this is just a general setting. There's not.
Okay.
And field body local just means
So
it's these H's are field body local.
Okay, thank you. Yeah.
Okay, so now we have defined local minimum problem. We can now ask for, if we now focus on local unitary perturbations versus thermal perturbations, what is the complexity for solving local minima problem? So first, let us look at the simpler case of considering local unitary perturbation. Particularly, it's not hard to prove the following proposition, which states that the problem of finding local minima under local unitary perturbation is classically easy. Actually, it's classically trivial. And the reason that this is true, which means that there's no quantum advantage if we focus on this problem. And the reason that this is true is one can easily prove the following lemma, which states that for any local Hamiltonian, like really any, a random state sample from the entire Hilbert space uniformly would be a local minimum of H under local unitary perturbations. It's not that hard to see, because if we have a random state, then when we look at its local reduced density matrices, it would just all be maximally mixed. So now when we perturb them using these local unitary, there will still be maximally mixed. And hence the energy will not change. And hence all of these random state, they would all just be local minimum. And the right picture for this is really like this barren plateau picture from variational quantum algorithms, where for the majority of the state, it would just all be flat. Like when we do any kind of perturbations, the energy would remain unchanged. Only until we're quite very close to ground state, then there will be some non-trivial landscape. And what that means is that the classical algorithm can just essentially say, the maximally mixed state is or just a random state is a local minimum, and hence it can find it very efficiently. So what this shows is that while local unitary perturbations, they're mathematically natural, they're not physically well motivated, and they have this kind of strange landscape picture. And now what we like to do is to see how the conceptual picture changes when we consider thermal perturbations instead of local unitary perturbations. So first, before diving into that, just there's a theorem that one could first show, is that the problem of finding local minima under thermal perturbation, it would be quantumly easy. And the way to show that is just essentially applying gradient descent based on these thermal perturbations. So it's a combination of these thermal Lambda assimilation and gradient descent. And one can easily use that to show that, like, you start from any place, say the maximum mixed state, and now one just run these, one consider these different possible Lambda perturbations, calculate the gradient, and then just walk in a direction. And within a polynomial number of steps, one can prove that it will converge to a local minimum. So the convergence is proven because of some smoothness property that one can prove regarding the second derivative of thermal Lindbladians. But then, even though we have this, while this problem is quantumly easy, one might also question whether this can also be classically easy, like in the case of local unitary perturbations. And to answer that question, what we're going to do is we're going to focus on some special families of Hamiltonians on 2D lattices, essentially a modified version of Delft's circuit Hamiltonian construction, where the ground state of these Hamiltonians would encode the output of the circuit, C. So finding the ground state of these Hamiltonians, it would be BQP hard. But then perhaps finding local minimum of them can be much easier. For example, if we wanted to find local minimum under local unitary perturbation, like the one we just talked about, then that would still be very easy for these HC. Because for any local Hamiltonian, the landscape has a large barren plateau, and hence finding local minima is easy. So what we need to do is to say that there's no classically easy local minima that is lurking in this exponentially large Hilbert space when we focus this on thermal perturbations. And in order to achieve that, the main technical or the most technically involved contribution of this work is the following theorem, which states that if we now look at this energy landscape associated to these 2D lattice Hamiltonian, the special ones, then one can prove that all approximate local minimum of HC under thermal perturbations are close to the global minimum, which is the ground state. So even though in the case when we can only do closed system perturbations or closed system dynamics, there will be a large barren plateau. When we consider thermal perturbation for these families of Hamiltonians, we can prove that there's no barren plateau, there's no bad local minimum, and no matter where you start, if you start from a Hall random state, if you start from excellently mixed state, no matter where you start, when you just cool it down, it will go to the ground state. Okay, so now what I would like to do is just to quickly sketch what the proof looks like. So recall that these thermal perturbations, they correspond to having these local operator AA. But then the perturbation is done by first creating these thermal Lindbladians that corresponds to how the like weakly coupling to the environment and tracing out the environment. And then these Lindblad jump operator are the actual action that will happen to the system. So in the local unitary perturbation case, one can just again think of the same set of local operator. And what one would often see is that if the system is too entangled, like it's a random state, then these local operator would not change its energy. However, when we have this Lindblad jump operator, so something nice happens. So first of all, these Lindblad jump operator, they're indexed by this omega, which has an energy unit, and it measures the energy difference. But more precisely, what these Lindblad jump operator does is the following. So suppose that we have these local operator, think of them as the local interactions that couples the system and the path. If we just expand it out in terms of the energy eigen states of the Hamiltonian H, let's say after expansion, it looks like this. It's not hard to show that the Lindblad jump operator corresponds to an object like this. So it's essentially just filtering out the transitions in the original local operator, where the energy difference is close to omega.
Sorry, these operators are very non-local, right?
Yes. Yeah. So the original AA, that's a local one. But then after like if now the environment is in place and then it's interacting, weakly interacting, and then we retrace it out, it would create this object that can be very non-local.
Still quasi-local, right?
Yes, for when beta is not too high and tau is not too long, then it will be quasi-local.
Where's beta?
Beta would not, yeah, beta would So these are the jump operators, and beta would only appear when in the kind of how often does each of these jump operator occur?
Beta has nothing to do with the quality of pattern of this jump.
I see. That's indeed true.
And this is a Davis type, and this is a Davis type. And you can do this because the energies are multiples of it.
You mean later on?
Yeah, the EIs, they are well spaced.
Yeah. Later on, we were gonna set it up so that they're well spaced. Otherwise, there would be some trouble.
Yeah. So
Yeah.
since it's a Davis type, why since it's quasi-local?
Because energies are well spaced, you can do a smearing argument,
Oh, I see.
replace it with it.
Okay, good. Yeah.
So if we now look closely at this object, we can see that basically what was happening, or where the power of thermal perturbation come from over local unitary perturbation, is that to suppose these AA are the perturbations, the local unitary perturbations, they could have matrix element. Like suppose we look at an eigenstate, it would have matrix element to energy eigenstate that have higher energy or also lower energy. And when we start from a random state, then there will be contributions going up and down that kind of equally canceled out, and hence at the end, the energy doesn't change, and that's where this barren plateau comes from. However, the nice thing about the Limbaugh jump operator for omega less than 0 is that it induces transition from EJ only to lower energy, so it filters out the one that's jumping up. So if for every energy eigenstate EJ, there exists some local operator AA such that, and also a lower energy EI, such that the transition from EJ to EI through these local operator is not equal to 0, it's sufficiently away from 0, then the whole landscape would not have a suboptimal local minima. So one can kind of understand this by relating it to classical combinatorial optimization. So in classical optimization, these EI, EJ, they're just bit strings. And if for every bit string, there exists a local kind of bit flips operation, bit flip action, such that it will change it to one with lower cost function, then the system would not have suboptimal local minima.
So is this fair to say this is like, I mean, as long as the Markov chain is connected, you will always go to the, I mean, like equilibrium distribution, something like that.
Yeah, I think it's related, can be understood as that.
Go to local bit. No, I mean, there's no local minimum. It's only local. As long as it's connected, it's only one.
Yeah. If this holds, then there's no suboptimal ones. It would just be the ground state.
It's a similar question. Is this like a ergodicity? So in open consistency, ergodicity means you can get any state to another state.
Yeah, I think it's related. It's like the different energy eigenstates are all well connected through these local operators. So you would not have some energy eigenstate such that all the local operators would only would only go up, and it would. I wouldn't say it's that close to, or it's in a way related to ergodicity, but it's more about like, can you keep finding directions that you go down?
So there has to be some specific structure between the local perturbation of the AA and the Hamiltonian.
Yes.
You have symmetries where certain local operators don't have matrix element, so what's the assumption that allows you to avoid that?
Yeah, you mean like how does one? So we have some general characterization, but I would say in general it's still not clear. There are Hamiltonians one can easily construct where this is not true. Essentially, the Hamiltonians that correspond to these QMA hardness, this would not be true, because if this is true, then there would not be a QMA hardness. So for QMA hard Hamiltonians, like the original circuit Hamiltonian construction that Kitaf constructed, that this would not satisfy.
In some sense, the previous setting is like a nonlinear problem, but this is just a linear problem. With the unitary perturbation. Because really now you just work on the density matrix and you find it just linear operation.
In a sense, yes, but previously the local terms, they would also just generate the linear operator on the state space, right?
Like the parameterization of the over the all the choices you can pick.
Yes. Yes, but here it's 2. Because these are the choices are these AA. And the way AA come into play into the Lambodian, they're quite complicated. Like if given these local operator, the Lambodian that come out of it, which is the one that will actually act on the system, those perturbations, like if one look at end to end, it will also be quite nonlinear. Yes.
So it's like, I mean, there is a certain assumption of something coming from here, which is the fact that the path has a range of energies that spans the spectrum. So for certain paths, you might have spectral densities that don't actually allow you to make transition between very big gaps in energy. Now, having Lambodian, assume that you don't have that and you have a flat spectrum across the whole spectrum of the Hamiltonian, but in reality, paths don't have fully flat spectrum.
I see. Yeah, I think here we're just assuming like an infinitely large path and it has
With infinite time duration.
Yes. This tau actually kind of characterizes that time scale. Yes.
Okay.
But we are gonna take tau to be like polynomially large. So yes, it will be quite long. If tau is not low enough, then I think something like what you're saying, like it would not be able to discern energy well enough and so on, and it would not causes some of these jump to behave so nicely. So that does happen.
So just a question for, I mean, I think you stated 2 theorems there. One is that finding local minimum is quantumly easy.
Yes.
And then you're also saying that local minimum is essentially global minimum.
No. That's that second theorem only holds for this specific family that we were studying. It doesn't hold in general.
So what's the condition that like exclude that like a QMA?
Yeah. So for example, this condition, like this.
Oh, so this is the assumption.
Yeah. This is
okay.
the assumption, and then we need to essentially prove this for the family that we're looking at. And if we now just look at a QMA hard Hamiltonian, one can show that this will not hold. Yes. Oh, okay. I'll speed up a little bit. So essentially, like, so here I'm just gonna quickly go through the circuit Hamiltonian construction. We have some circuit C that can be written out as a unitary. That's a product of these 2 qubit gates, U1 to UT. Then the Hamiltonian HC will consist of these 3 Hamiltonians, will be a sum of these 3 Hamiltonians with a unique ground state that's given by that. So the way one should understand that is this is the clock register that kind of, the clock ticks based on how many zeros are in there. And then the rest is like the state in the intermediate computation. And in order to ensure this a Bohr frequency gap that Lyndon just mentioned, we have to, the ground state is being designed so that there is this binomial factor, which is not there in the original circuit Hamiltonian construction. But basically what we showed is that first there are, if we just focus on the clock, the clock part, the edge clock, which just kind of checks whether this clock behaves correctly in the sense that it's always starting with a bunch of 0 followed by a bunch of 1. Because that Hamiltonian is very simple, one can just directly prove that there are no suboptimal local minima in that Hamiltonian. And then what we also show is that if we are now in the ground state space, because there's a large degeneracy of this edge clock, there are no suboptimal local minimum if we look at the sum of these 2. And finally, if we're focusing on the ground state space of these 2, then there are no suboptimal local minimum in the sum of all 3. So note that this just kind of, each of these are are relatively easy to prove. It's because we're just working in the ground state space of some of these, which greatly simplifies the structure. For example, in the ground state space of these 2, it corresponds to essentially like the clock is behaving correctly and the propagation is also operating correctly, and we just kind of need to check the input part. And now what one needs to show is what we essentially prove is kind of a meta theorem that says if there's a Hamiltonians that have a large Bohr frequency gap, meaning that when you consider every possible pair of energy eigenstate, like the difference between them, they will the gap between them, the gap of these different differences. So it's like the minimum difference of energy differences. That's the Bohr frequency gap. If that Bohr frequency gap is sufficiently large and the statement 1, 2, 3 all holds, then one can prove that there are no suboptimal local minima in the sum of these three, the whole thing, in the whole landscape. Yeah, these are a bit technical, but essentially the etch-in is standard, and then we set up the etch clock so that it has some non-uniform magnitude. So the local excitation have the tendency to move to the right, and it will cancel itself out. And then we set up the propagation part to have an energy spectrum that's integer valued. So then the Bohr frequency gap is always just 1. And that gives rise to this kind of strangely looking binomial factor, but that's still fine in the arguments because we can kind of set up the computation to mostly happen in the middle part of the kind of the bulk part of this binomial distribution. And then together one can prove this theorem, which implies that because the ground state of these HC, they are classically hard, it immediately implies that the problem of finding local minima under thermal perturbation is classically hard if BBB is not equal to BQP. And one corollary of this is that there are 2D Hamiltonians where when we have some efficient classical algorithm that we try to optimize the energy, this can be strictly improved if we just take the optimized classical ansatz or classical state onto quantum computer and simulate quantum thermodynamics. And just kind of summarizing, we essentially show that finding local minima under local unitary perturbation is trivial for classical computation. On the other hand, if we just switch out these closed system dynamics as an open system dynamics, then finding local minima under thermal perturbation would be universal for quantum computation. And an immediate consequence of this is if I have a very good refrigerator that can cool systems to just local minima, then they are universal quantum computer. Now let me just quickly end with a few open questions. So here we've been studying local minima, which are indistinguishable from ground state under small perturbation. But one could ask, can we efficiently find states that are indistinguishable from ground state under any quantum algorithm with bounded runtime? And for example, could pseudorandomness help us answer this question? Another important question is that here we showed that there's quantum advantage in computing properties of systems that thermalize at very low temperature, but it still remains open if there's a quantum advantage in estimating properties of systems thermalizing at a constant temperature. For sampling from such systems, we know there are advantages. There's a nice work by Yunchao, Anthony, and Thiago on that, as well as some follow-up works. But for estimating properties, that is still wide open. So to conclude, in this work, we showed that finding ground state is, or it's well known that finding ground state is classically and quantumly hard. And here we showed that if we now switch out ground state, which is the global minimum, by local minimum in energy, then this is classically hard, but quantumly easy. That's it for my talk. Thank you so much for listening.
Wonderful. Thank you very much. Questions?
So in classical case, the way it's defined, usually finding whether a state is a local optimum or even finding a local minimum is usually a hard problem, hard or something. So here, are you avoiding that because you're not finding a minimum, but you're on the way to finding something that's minimum, or is the definition now sufficiently constrained that it's actually easy?
That's a great question. So we were looking into that because we were kind of puzzled by claims in the classical TCS literature that says finding local minimum is hard. Scott Ernst also have papers on that. And the reason is actually the following. So here we focus on the cost function to be defined by a local Hamiltonian, which has a magnitude that's polynomially bounded. So in the classical case, I think when people talk about local, like finding local minimum, they consider the cost function to be in a way unbounded. So they just assume that you have a circuit, like given a current state there's a circuit that computes an output cost function that can take values up to exponential. So the thing there is that if you just do normal grade, like naively, intuitively, it felt like, intuitively, if you just do gradient descent, then you should just be able to find a pretty good local minima. And the reason that, but on the other hand, if the cost function can take exponentially many values, then this can just keep going on for a very, very long time. And I would say that's, from my reading, it seems like that's one of the key way where they allow they kind of, the hardness comes into play, is that the gradient descent might just not converge, because every time you improve by 1, but then you need to improve by exponentially many times in order to reach a local minimum. Or another way to say it is like if you just compress it down, it's like you wanted to find a almost exact local minima rather than finding an additive error approximate local minima.
But don't you also have this other issue there where you have exponentially many directions of the motion, and then you might be, you might get a plateau with respect to most of the directions, except very few where you can make an improvement.
Yeah, if one defined the possible actions to be exponential, then that would also be another cost. And here we're only focusing on the perturbations to be polynomial, and that's another way that works.
All right, wonderful. Now we're kind of running a bit over time, so how about we leave all questions for the break? So we'll have ideally a 15-minute break, but it's probably going to be closer to 10. So I'll see you guys back in here shortly, and let's thank Robert one more time. And oh yes, and we'll be back in here for the panel discussion, where I promise I won't be as much of a jerk as I usually am.